Good morning, Advanced Chemistry. Today we're going to take some notes on Learning Target 1.5, which is called colligative properties of solutions. So there's 4 bullet points here, and one thing I want to mention is that in your original set of learning targets that I gave to you, this was not the 5th learning target, because the 5th learning target I felt we talked about in some of the other learning targets and last year, and I wanted to include something that was some new information or some newer information. So I chose to replace it instead with this one. I will make that update to the learning targets that are on your shared folder in Google Drive that I taught you to get to yesterday. But basically I have 4 bullet points here. We have describe what's meant by vapor pressure of a solvent and describe how this changes as a solute is added. So we're going to spend some time today talking about vapor pressure and what that means. We're going to describe how and why adding a solute to a solvent changes both the freezing point and the boiling point of a solution. We're going to mathematically determine the temperature at which a solution will boil or freeze given what's known as the molal freezing or boiling constant, Kf or Kb. And we're going to determine the the molar mass of an unknown molecular solute using laboratory data. So here we go. Starting with, let's talk about what a colligative property is. So the definition of a colligative property is a physical property of a solution. So as opposed to a chemical property, it doesn't change what that solution is or the chemicals in that solution. They are physical properties of solution that depend on the number of solute particles, but not the identity of the solute particles. So that all comes down to concentration. And concentration in this particular sense for colligative properties, they don't use molality for some reason. They use instead the number of moles per kilograms of solvent. So they use moles of solute per kilograms of solvent. And that is known as molality, as opposed to molarity, which is moles of solute per liters of total solution. Now we've got on the bottom kilograms, the mass of the solvent. Just the solvent, not the entire solution. So molality is abbreviated small m, and its units are moles per kilogram. So we're going to talk some more about molality in a while, but for colligative properties, for some reason, the concentration unit is not molar, but molal. If I'm going too fast, feel free to pause here as we're moving along. So it's a colligative property because it depends not on what it is, but how many solute particles are in solution. Here are the 4 colligative properties that we're going to talk about. So these are the 4: vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. You don't have to write these down all right now if you don't want to, because we're going to talk about each one at a time. So we're going to start with vapor pressure lowering. That is the first. And vapor pressure lowering is actually responsible for B and C. So we're going to talk about how it is that because you have a vapor pressure that is lowered, it's going to affect the freezing point and the boiling point of a solution. Alright, so let's talk about vapor pressure. Before we do that, a reminder about the Vant Hoff factor, or I. We talked about this. The Vant Hoff factor is the relative number of particles in solution per 1 mole of dissolved solute. And we abbreviate it with like this italic I, or sometimes a cursive lowercase I. For all covalent compounds, so something that's not electrolytic, it's not going to conduct electricity, there's not going to be ions in solution, the I value for a covalent compound is going to be 1 always. So something like table sugar, which is C12H22O11, because that is covalent, so no ions in solution, that is going to have a Vant Hoff factor of 1. But then we had talked about ionic compounds that are electrolytic solutions that are going to dissociate, and those, it depends on how many moles of ions you have in solution. So for example, if you have MgCl2 and that dissolves in water, you would have Mg plus 2 aqueous and 2Cl minus 1 aqueous. Your Vant Hoff factor would be the sum of all your coefficients of your ions. So we have 1 magnesium ion and 2 chloride ions, so the I value is 3. Okay, so now that we've reviewed Vant Hoff factor, let's talk about vapor pressure lowering. So the definition of vapor pressure is as follows. It is the pressure exerted in a closed container by liquid particles that have escaped the surface and entered the gas phase. The pressure exerted in a closed container by liquid particles that have escaped the surface and entered the gas phase. And then I have a little note here. The more volatile a solvent, the more vapor pressure it is likely to have. And then the weaker the IMFs of the solvent, the more volatile it will be. So that's kind of a sub-statement. So for example, if I have a container here that's closed, and in the bottom, let's say it's a 1 liter container. And in the bottom here, I have about 300 milliliters of water. Some of these water molecules along the surface, no matter what the temperature is, are going to escape. So let's just say it's room temperature, so about, a little above room temperature, maybe 25 degrees Celsius. Well, 25 degrees Celsius, some of these molecules are going to escape the surface. So we are going to have some water molecules that have evaporated and are bouncing around the walls of the container, exerting a pressure on the side of the container. And let's just say that the pressure in that container is, we'll call it 1 atmosphere exactly. So if that pressure is 1.0 atmospheres on the side of the container, that's the vapor pressure. So now let's do the same thing, and I'll use a different color here. And I'm going to choose a different solvent. So instead of water, I'm going to have the same situation here, 25 degrees Celsius, closed container of the same size, so 1 liter again. But in the bottom now, instead, I'm going to have 300 milliliters of, let's say this is acetone. And acetone is like pretty much the main ingredient in nail polish remover. Pure acetone is something that's very volatile, and you know this because if you spill it on you, it evaporates super quickly. If you were in my class last year, we did a lab where we streaked it across the table and it evaporates almost instantly. So this is much more volatile, and that has to do with the fact that its intermolecular forces are a lot weaker. So, you know, at the risk of talking a little too much here, water has hydrogen bonds, which are very strong intermolecular forces. Acetone does not. Acetone is polar, so it has dipole-dipole intermolecular forces, which are much weaker, and it is much more volatile. Meaning, if you have the same amount, those molecules are a lot more likely to leave the surface. So you'll have many more acetone molecules in the gas phase. And those acetone molecules will all be bumping around, creating pressure. So because you have more molecules exerting a greater pressure, then the vapor pressure is also higher. So whereas over here we had 1.0 atmospheres with our 300 milliliters of water, this would be somewhat greater than 1 atmosphere. So this would have the higher vapor pressure of the two. So it has to do with those liquid particles that have escaped the surface and entered the gas phase. So it turns out when you take these solvents and you dissolve something in them, that's a colligative property. So when you add a non-volatile solute, so non-volatile meaning does not become a gas, and we're going to assume that all our solutes are not volatile, that is going to lower the vapor pressure of a solvent. It just always does. And we're not even going to get into why, we're just going to say that it does. So adding a non-volatile solute, and so I'll just make a little note here, non-volatile means will not escape solution. That is always going to lower the vapor pressure of that solvent. So back to our water example here. So if we had that 300 milliliters of water, and that was our solvent, and we said that was about, and we're just totally making this up, but 1 atmosphere of vapor pressure. If you were to do the same thing, and the solvent is water, but now it's 300 milliliters of 0.1 molar sodium chloride solution that's aqueous. So water is still my solvent, but now I've got 0.1 molar sodium chloride in there. Now the vapor pressure is going to be somewhat less than that. So for whatever reason, water molecules, and I know what the reason is, we're just not talking about it now, but because of that solute in there, the number of water molecules that can escape is lowered. And the number of water molecules over here would be greater in the pure solvent. So that's the basic idea behind vapor pressure. Let's talk about some consequences of lowering a vapor pressure. And so this has to do with boiling point elevation and freezing point depression. So in order to understand how vapor pressure influences boiling point and freezing point of a solution, we need to define what boiling point and freezing point mean. So let's define boiling point. The definition of boiling point is when the vapor pressure of a solution is equal to the atmospheric pressure so when the vapor pressure of a solution becomes equal to the atmospheric pressure, so just like air pressure, the air pressure around us, then a solution will boil. So the vapor pressure is equal to atmospheric pressure. That is a solution's boiling point. So something like acetone, for example, can do that at a much lower temperature than water. So it takes a lot less energy to get those molecules up and out of the gas phase than it does those water molecules. The definition of freezing point is when the solid and liquid phases of a solution are in equilibrium with each other. And to explain that just a little bit more, when the solid and liquid phases of a solution are at equilibrium with each other, just think about an ice cube. So at 0 degrees Celsius, which is the freezing point of water, we should have ice at 0 degrees Celsius surrounded by liquid water at 0 degrees Celsius. And so what would happen is that at 0 degrees Celsius, ice is melting, but liquid water is also freezing, and they're doing that at equal rates. So every time one water molecule becomes a liquid from ice, one liquid molecule of water is becoming ice. So it turns out when you warm that up, let's say to 20 degrees Celsius, if you have a chunk of ice at 20 degrees Celsius, and then we have liquid water, obviously we would have a lot more molecules becoming liquid water than we would have liquid water becoming ice at 20 degrees Celsius. So I have a little tiny arrow to show liquid water becoming ice. But obviously, the solid going into the liquid phase is much greater rate. On the other hand, if I came over here and I was at negative 15 degrees Celsius and I had an ice cube surrounded by liquid water, I would have a whole lot more liquid becoming ice than vice versa. So that's what equilibrium means. It means at the same rate. So ice is becoming water and water is becoming ice at the same rate. So that's what the freezing point is for a solution. So let's talk about how this all comes together now. And I think this is one of just the coolest things in chemistry is this colligative property and how vapor pressure affects boiling point and freezing point. So what we're going to do right now, I want you to think about a closed container of water. So I'm going to draw it up here just for visual. So just like we have been talking about earlier, our 300 milliliters of water in our closed container. And the number of water molecules, remember, in the gas phase is going to determine our vapor pressure. So if we have a spot right here where our water, I just lost my drawing. Let's say we have water at 0 degrees Celsius. So this will be 0 degrees Celsius. So right there for water, it's not a very good dot, right here for water represents our freezing point at 0 degrees Celsius. So let's draw just a dotted line to show that that is solid. And then from here, as the temperature goes up, those water molecules are going to have more energy, and the vapor pressure is going to go up. I don't know why I'm having so much trouble with this. So 0 degrees, it's going to go up until it hits this dotted line, which I have chosen to represent the atmospheric pressure. So this is pure water with nothing dissolved in it. So this line right here is atmospheric pressure. When we get to that point where it intersects atmospheric pressure, that is the boiling point. So right there, that should be 100 degrees Celsius for water. And this would be 0 degrees Celsius for water. So right here we have our solid phase, and then obviously throughout this whole line right here we have our liquid phase, and then right here it becomes a gas. We don't really have vapor pressure anymore because there's no liquid to exert the pressure. It's just all gas, so it's just the pressure inside the container. So this is what vapor pressure versus temperature looks like. So the vapor pressure of something is going to increase if we heat it up, because again, if you think back to our box, more at 0 degrees Celsius, if I heat this up, more molecules are going to have enough energy to evaporate. So the higher the temperature, the more water molecules are going to evaporate, and then your vapor pressure will increase. When you get to the point where this vapor pressure is going to meet the atmospheric pressure around it, then it will actually boil. So we've got our boiling point and we've got our freezing point. So I'm just going to mark those real quick. So here's our BP and here's our FP. Okay, now I'm going to choose another color and I'm going to show you what happens if our vapor pressure lowers. So pure water, no solute. I'm going to draw another line if we have water, let's say with salt, for example. So we know that that means the vapor pressure will lower. So at every point along this line, the vapor pressure should go down. So this point right here will instead be right here. So our whole vapor pressure line decreases. So it goes down at every single point on the line. And if I extend this line, we can see what happens to the freezing point and the boiling point. Now, my line isn't perfect here, but the solid and liquid, we can see how the boiling point and the freezing point have shifted. So now, where this intersects the atmospheric pressure is way up here. The new boiling point is much higher, at a much higher temperature than it originally was. Same thing down here, the freezing point has become much lower than it originally was, just because of the fact that when you add the solute, so with solute, I managed to erase that there, that vapor pressure line lowers. So lower VP, because that's a colligative property, and because of that, our boiling point is higher, so it's elevated, and our freezing point is lower. There's another ramification here that I think is very, very interesting, and that's if I take away the vapor pressure lowering line. So let me get rid of that. And if I draw in just, again, the pure water line, so I have 0 degrees Celsius here, and then water increases its vapor pressure until here, and then when it is equal to the atmospheric pressure, it boils, and that's at 100 degrees Celsius. So here is the atmospheric pressure, we said. And here at, not too far above sea level in Michigan, our atmospheric pressure is right around 1 atmosphere. But if you were to go to Colorado, for example, and live up high in the Mile High City in Denver, then your atmospheric pressure would be significantly lower than it is here in Michigan. In fact, if you've ever visited out there, you may have even gotten ill because it has that great of an effect on people. And sometimes athletes go there to train because there's less air molecules to deal with, and it helps them adjust, blah, blah, blah. So regardless, what this does is if you're on top of a mountain, it lowers the atmospheric pressure. So I want you to look at, if we're still talking about pure water without anything in it, and I keep my vapor pressure of water the same, so this would be atmospheric pressure in Denver. So if I'm in Denver, my atmospheric pressure line is going to decrease, and I have lower pressure there. Look at what happens to your boiling point. The boiling point for somewhere at a high elevation like this is going to be significantly lower than it is here at sea level. So if you've ever looked on the back of a box of cookies or something like that, like pancakes or waffles, there's some high altitude cooking directions. And what's usually on there is it means that you have to cook something for a longer period of time because water... So I want to leave you by talking about something that I think is very interesting, and that is the fact that when I have pure water, again, so no solute in there, and I think about what happens at this boiling point if I change the atmospheric pressure. So we've just talked about atmospheric pressure being this kind of arbitrary dotted line, and here in Michigan, where we are just slightly above sea level, our atmospheric pressure is pretty normal. But if you're to go to the top of a mountain, for example, like in Colorado and Denver, the air pressure would be significantly lower. In fact, if you've ever visited out that way, a lot of people get sick because the pressure is so much lower. It takes their body quite an adjustment for their body. But anyways, if I lower this line, so not by adding anything, but it's still just pure water, but if I lower this line because I am somewhere where the air pressure is lower, like Colorado, I want you guys to see what happens, what that effect is on the boiling point. So this is our new atmospheric pressure. So this one is Michigan, and then this one is Colorado. Our intersection between vapor pressure and atmospheric pressure is now much lower than it was before. So originally it was here at 100 degrees Celsius. This might be something like 97 degrees Celsius. So what's interesting is that water actually boils at a lower temperature when you're on top of a mountain because it reaches this intersection more quickly. It doesn't take as much heat energy to get those water molecules to meet the atmospheric pressure. So if you cook something in Colorado, if you have like a box of, I don't know, brownies or something, on the back of the box, here's your brownie box, brownies, you have some high altitude cooking directions, because when you're at a high altitude, you have to do things a little bit differently because your water and anything that's going to boil is going to do that quicker, which means you'll need to cook it longer because it's at a lower temperature while it is cooking. So I just think that's really interesting and very relevant. So I think that is it for now. I hope to be back with you tomorrow. If you're watching this with a sub, I have a sick daughter, so I will see you tomorrow and we will continue our work on the lab. But other than that, have a wonderful day and I hope to see you very soon. See ya.